There we go.
We
Welcome
are.
to Absolute Zero. I'm Rachel Pell.
And I'm Bertrand Leroy. This
Today,
is the first live episode that we are doing. It's going to be the first.
yep,
Um, we are a science show, science talk show, right? We're going to talk about science. Um, we've actually recorded a lot of episodes already, but we're starting with a live event today because of news that came up yesterday
yeah.
about detecting gravitational waves, and we thought this was the perfect opportunity to actually get the show started. Even though we've actually been doing that for a
For a
year
while.
or so,
Well,
right?
yes, plus we can release those when we're slacking off.
Yeah, exactly. So that's the idea. We have a bunch of shows, about 30, that are in store and that we're ready to use at any time. Uh, in the cases, yeah, where we can't do the show live. Um, okay, so we should probably say a few things about one, who are we and what we're going to do on this show.
Yeah.
Um, so I'm Bertrand Leroy. I work as a program manager during the day, and I have a background in physics. I have a PhD in physics, so I know a few things about gravitation, about quantum mechanics, and a few things like that. And I'm a huge science geek, so that's me. What about you, Rachel?
Yeah, I'm Rachel Appel, and I'm basically not pedigreed or anything like that. I did have some college in computer science, and then I work, of course, as a software developer, so I kind of stayed in that area. But I'm a science geek too. I like to nowadays that there's actual courses you could take online for free. I take advantage of that. Who says I get a free education, the ones that all the politicians talk about, whether they're for or against it. Just that I'm not getting a certificate at the end. That's just kind of an autodidact. So,
Yeah, so actually, we are not necessarily huge authorities in science.
right.
It's not our day job, but we are interested in science. We are skeptics, and we are trying to. We are going to try to have entertaining chats about science.
Right. Right.
We're going to take questions from the audience as well, and we're going to pick a topic every week. We're going to discuss that topic and usually go hugely off topic and end up talking about something completely different. So we hope this is going to be entertaining for everyone, and well, we'll see where that goes. So how about we talk about yesterday's news already,
Right.
which are gravitational waves.
Yeah. So apparently, some researchers have found gravitational waves. They've actually been able to measure or see them. I'll use the word see. I don't know if that's quite the appropriate word, but they have this really interesting device that's, from what I gather, like 4 kilometers long, like two tubes, and they do some very fancy technical things to be able to determine these waves. And there's, uh, quite a big deal because it confirms Einstein's theories. And
Once again,
yeah, once again, so that's kind of great. And it actually opens up a whole lot of cool science that can happen now. So, and I'm sure you know more about this stuff than I do because some of it went over my head when they started getting released.
yeah, so I'll try to give some context and some explanations about exactly what happened. So we call them gravitational waves. Actually, I think we should name them space-time waves because that would be more impressive and closer to what's happening here. So basically, when you have something like electromagnetism or sound or what happens at the surface of a lake when you hit the surface, uh, all those are waves, and they are waves because they are perturbations in a field. So a field is um, a quantity that has a different value in every point of space, right? That's a basic description of a field. There are various types of fields. There is what physicists call scalar fields, where you have a single value for every point in space. And there are vector fields, and then there are tensor fields, and there are different kinds of fields where the values are of a different nature. In the case of electromagnetism, which is basically a fancy way of saying light, you have the electric field and the magnetic field that are two vectors that can vary in every point of space.
I was going to say, I think most people have heard of the electromagnetic field, at least.
Yeah, that's what it is.
Maybe a few others, yeah.
Yeah, and then you usually have a wave equation, and a wave equation is describing how the value of that field can vary from point to point and from instant to instant. Okay. And so that's the theoretical framework for waves and the fields. In the case of gravitation, you could imagine, with classical Newtonian gravitation, where, masses just create that potential in space, that energy potential, and then that translates into forces. You could imagine if that potential actually propagates at the speed of light or at any propagation speed, you can imagine that if you move a mass, you would actually create waves in the gravitational field.
Right.
So in principle, there is no obstacle to having gravitational waves, even if you only have Newtonian gravitation.
Right.
But this is not what we are dealing with here. What we are dealing with...
Masses don't really move like that, do they? Mm-hmm. Masses don't really move like that.
Well, you could take a mass and make it move, and that
would, but they generally don't naturally, right? They just kind of orbit.
Yes.
Yeah.
So what's different here is that we are talking about waves in the fabric of space-time itself. And this is not just proving that gravitation can propagate as waves. It also proves that those waves are actually compressing space in interesting ways.
Oh, okay.
So what was observed here is, as you said, so the observatory here is made of two big laser tunnels where you have big laser beams being shot. And those tunnels are 4 kilometers long. And then you have interferences between those two beams. So basically, you shoot those beams, you bump them against mirrors, make them come back, and make interferences. Okay, and if the distance in one of the arms changes, then this beam here is going to come back a little sooner or a little later. Okay, and because it does, it will be at a different phase when it hits the point of interference in the middle. Okay, so because of that, when the gravitational wave arrives onto the observatory, the space that is occupied by those arms is actually going to vary. So
it should vary a little bit depending on how the wave comes through, maybe on one arm and then the other.
Yeah. So you're going to have one arm that is going to be compressed, the other arm that's going to be expanded.
Literally like putting people in a stadium and having them do the wave.
Yeah.
Arms would kind of go up and down.
Mm-hmm. Yeah. And so the way interferences work is that to get the amplitude of the wave at a given point, you just add the various waves that come in. And when they are opposite, they would cancel. And when they are in sync, they would add up, right? So you would have more light or less light, depending on where you look.
So, and if you measure this down to, I read what it was, but it was a crazy small number, like a billionth or some ridiculous thing.
Yes. So the problem is what makes gravitational waves so difficult to detect is that we're actually dealing with minuscule variations in distances. Yeah. And we said that the arms were
though. They
So,
start off pretty big, right? And just like a wave, if you throw a rock in a pond, it kind of gets that ripple effect and gets
yeah,
smaller.
and
So,
those things are happening very, very far away. So those waves are attenuated. And we'll talk about the huge amplitude of those waves at the point where they are emitted. But when they reach us, they are minuscule, and they will translate to variations in distances that on this 4 kilometer arm correspond to less than the size of an atom nucleus.
right, which is tiny, small, and crazy. And
And we have the technology to
to
detect
do
that.
that, it's pretty crazy. Yeah.
That in itself is
Earth
amazing.
science, I know, right?
The engineering behind that discovery is incredible. And
Yeah, I don't know if I'd have the patience to make a device that can measure something that small, right? That's just very,
yeah, do you
that's
know
very
how long
painstaking.
we've been
It's been a long time, right? They were working
yes.
on this alongside like some of the Hadron researchers, weren't they?
So
I got
when I was a student, I almost worked on one of those, and that was more than 20 years ago.
oh, now you're just aging yourself here.
Yeah. But yeah, those guys have basically been working on that stuff for more than 20 years. And so far, they've seen nothing. So can you imagine working on something for 20 years and having no results at all?
Right. And then one day,
And then one day, you make the arguably the most important discovery in the century so far.
yeah. Yeah, it's pretty good one. Yeah, somebody was asking about, well, they spent like $6 billion or whatever astronomical amount this kind of stuff takes to do. What good is it going to do? Well, if you think the first thing I thought is, all right, they could detect the waves, and now we know where these waves are. Just like a ship with sails, we might be able to build a ship that can travel vast distances in space by floating on these waves or riding waves like a surfer would or a ship would with sails. Maybe not literally like an actual pirate ship for outer space, but using some of those same concepts, right? The dynamics of how waves work. There may be implications for time travel, I would say, and also venturing back to finding out what the origins of things are, the universe.
Yeah, so I think the most important applications will be in understanding more about black holes, which are very difficult to observe with light because there isn't much except for the disks that are around it. So the way we observe black holes today is by looking at what rotates around them, like, for example, at the center of the galaxy. Now we have a direct window. It's like actually looking at a black hole. Well,
Right.
in this case, at two black holes. The other application is going to be cosmology. And maybe a third one, this might actually help us understand what quantum gravitation is going to look like.
Oh, cool.
So essentially, this is a whole new field in physics. It opens a new window on the universe. And questioning it is like, going behind Galileo and asking him, well, what is this for?
Right.
What are you going to see? I don't
Yeah.
know.
When I hear questions like that, I kind of think of people going, "Ugh, so what are these stem cells like? Why would you spend all that money on finding out that we have such a thing? We
Yeah.
got cells. Gee,
Uh,
can you imagine? Well, there were some good things, right? And there still are, you know.
yeah.
Yeah.
Um,
Yeah, I'm just kind of envisioning more of the sci-fi kind of things, like where you can maybe time travel or those kind of fantastical things that can come out of the research. But the actual real like hardcore stuff would happen with what you're saying, right? The cosmology, uh, quantum mechanics and things like that um, are going to be the first things to start, these new fields opening right up.
yeah. And what's interesting about gravitational waves is that if you can detect them, that is super interesting because it enables you to see stuff that you wouldn't see with
Yeah.
light.
Yeah.
Um,
Oh, that's
because
something.
nothing stops gravitation. It just goes through everything.
Right, just being able to see all that extra stuff that's in the universe that we couldn't see now. And there's like giant objects out there that we discover that are whole new types of objects.
Yeah. So one difficulty is that you cannot observe any object with gravitational waves because you need a very specific set of circumstances to actually emit radiation of that sort. That, without going into the technicalities of gravitation, it's actually harder to emit gravitational waves than it is to emit light, for example, because you need to have certain symmetries that aren't necessary with other kinds of radiation. And in particular, you need to have an object that is, let's say that basically you need an object that is asymmetrical and that is rotating. That's an oversimplification, but that's pretty much it for now. So in this case, what they've seen is a couple of black holes rotating around each other, very, very close to each other, to the point where they actually fused into one big black hole. And that is an amazingly rare event.
Right, yes. Something we've not been able to observe so far.
Yeah, which is, well, yeah. And yeah, so there is that discovery as well, which it's the first time we are directly observing two black holes collapsing. That is huge in itself. So there are so many things about this discovery that make it completely amazing and mind-blowing.
There's one thing the black hole didn't eat up was news of this, the discovery of gravitational waves.
I'm sorry, what?
I said there's one thing a black hole didn't eat up is news of the gravitational waves.
Yeah. And there, I mean, yeah, there are so many aspects of this that are amazing. Another one that that blew my mind is that so those gravitational waves carry energy with them, right?
Yeah.
They're energetic by definition. It's a wave is energy moving around. Okay. And in that particular case, the energy that was carried away by gravitational radiation during the fusion of those black holes is about 3 solar masses in radiation.
Okay.
And because energy doesn't just go away, it means that those black holes, which are objects that are supposed to not let anything go out, and that is still true, but so that couple of objects actually, they are lighter now than they were before. And this is not black hole evaporation. It's that.
Oh, that's kind of weird.
Yeah. So you take two black holes that have a certain mass, you fuse them,
and they get lighter.
And they get lighter than the sum of their masses.
Okay.
Because they actually ejected some of their gravitational energy through radiation.
Okay.
Which is amazing.
Very counterintuitive at the surface of that, right? But once you think about, like, if they're ejecting, and then that's how we would detect it, right? Eventually those waves get here and our machine detects it. These little tiny waves, and then we can make the measurement.
Yeah, and so all this is general relativity, and if general relativity is doing one thing, it's explaining the interaction of energy and space-time. Black holes in particular are pure space-time in a way. They don't have any, they are not made of something, they are except space.
Yeah.
So the way they emit energy or absorb energy, all that stuff it's essentially about geometry, all of it.
I just kind of think of them as giant Pac-Men.
Yeah, do you think they go waka 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 waka?
That's what I thought happened.
When they eat stars.
Actually, they do that, right?
Yeah. Yeah, sure, of course. Yeah, so giant discovery. This is bigger than the discovery of the Higgs boson by far, in my mind. It's like discovering light in a way, or you
Right,
know, radio astronomy. That's something that you could compare. Uh, Using a kind of radiation that you haven't used before to look at the sky. And from the moment you open up that window, new objects, new phenomena appear, and you can't predict in advance what you're going to see. Um, when you look at the sky without using just the visible light, I mean, visible light is such a small part of the spectrum.
right,
So when you start looking at radio waves and different frequencies, you start seeing some amazing stuff, such as the background radiation of the universe,
yep.
which also was
Which tells a story.
completely. It's a revolution because it shows you what happened at the
Years
farthest past
ago. Yeah,
that you can observe. And this is the same. By using those gravitational waves, we're opening a new window onto not different wavelengths, but a completely different kind of radiation.
right,
And sure, we can observe only very violent phenomena such as black holes collapsing, or neutron stars getting absorbed by a black hole, or stuff like that, or the birth of the universe, which is the most violent event
them
ever.
all, I guess. Right? Yeah.
So who knows what we're going to see? That's
That will be cool to find out. And like my favorite thing that happens in science are the accidents. So when they're looking out there and then they stumble across something completely unexpected. So I can't wait to see what comes out of it as far as that, because there will be things that they'll be looking for specifically. But
yeah.
the little
So
pop-up things in
yeah.
science are like the best, I think.
For the moment, what's been announced here is so it's the result of decades of research and uh, incredible engineering, and they've
Lots of work.
seen what they expected to see, right? So we knew that, in a way, the news are not surprising to anyone who was following that field.
Right.
We knew that would happen, and actually, what would have been surprising would have been if we had seen nothing, right? We knew
Right.
that we would see something.
Right. And I
Uh,
actually read somewhere that the particular published results that are getting the attention right now have actually even been out for a few months, getting kicked
yes.
around before they became kind of a thing. And now it's all over the media, the
Mm.
science reporters. So,
Yeah, and that has to do with the way science news are created.
yeah.
Uh, People in the field are interacting openly all the time. It's just that science journalists don't necessarily see those. They don't necessarily
Right.
pay attention to those very theoretical papers that are
Well,
published and
I
so
could
on.
see where something like gravitational waves, somebody could easily skip past that thinking, oh, well, what's not been covered there already? If you're working as a journalist more so than a
Uh,
scientist.
so it's interesting to see how this particular one was announced. And it was similar to what happened with the Higgs boson. If you followed that field, you knew that yeah, it was pretty much done before it was announced. I mean, it wasn't such a big surprise if you had been following. But the details, are kept behind closed doors until those big announcements. And it's interesting how scientists do public relations. Uh, they don't suck at it, actually. That stuff made the news.
Right.
It made mainstream news. Everybody yesterday heard about gravitational waves, which are deeply theoretical topics. So
Yes. Well, so now that's something, gravity is just a theory. So, what does this all really mean if it's just a theory?
yeah, well, like evolution, gravitation is a fact and a theory, and a scientific theory.
Yeah, not just the layman's theory; it's an actual scientific.
Yeah, well, it's the law. Yep. What else about gravitational waves? We are going to have an episode about gravitation that is already recorded that we might broadcast
Okay.
one of those weeks. Do you have any questions?
Yeah,
We don't have that big of an audience right now, so we won't have many questions in the chat today.
Right.
Because it's the first episode and nobody knows us. But
Now, yeah, I think if they see the episode on gravity, it'll help a little bit with, if you're unfamiliar, the mechanics of just overall how it works and all
yeah. Yeah, so again, I think what's interesting here is not just gravitational waves, it's
right.
waves in space-time.
Waves in space-time, and this opens up the doors for so much more research, which is, pretty cool. And then again, you cannot reconfirm something too many times.
Yeah, so let's talk about the other confirmations of general relativity. Because not everyone realizes probably that this is something that has been verified many times.
Actually, didn't Einstein make some predictions that they reconfirmed again specifically?
Oh, yeah. Gravitational waves were a prediction that Einstein himself made. But there are others that were actually verified while he was alive, and actually even months after he published his theory. For example, one of the phenomena that general relativity explained is small deviations that Mercury had on its trajectory, and the way the precession was adjusted didn't fit with what Newtonian gravitation was predicting, and that's one of the things that general relativity predicts very accurately. So that was one of the first experimental verifications. The other one was the prediction that light would be deflected by a massive object.
Okay.
Because, actually, if you look at Newtonian gravitation, you will also predict that light will be deflected by a massive object.
Okay.
And the reason for that is that when you look at the trajectory of an object around another, it doesn't really depend on its mass. It depends on its velocity and the object of the attracting mass, the mass of the attracting object. So you would predict that if light is a limit case of massive objects, when you make the mass tend to zero, you will still see a trajectory that is not straight for light. So you would actually the idea of black holes predated general relativity. There is you can create you can imagine a Newtonian black hole where even light cannot escape because the escape velocity is more than the speed of light. And in the same way, you would predict a deviation of light coming from a massive object. But that deviation the prediction of the specific value of that deviation will be different if you compute it using general relativity.
Okay.
And very, very closely after, I think it was in 1912, something like that, they went to the North Pole and looked at an eclipse. And while the eclipse was going on, they measured how fast stars would disappear behind the sun and reappear. And you can only observe that during an eclipse, of course, because otherwise the light from the sun is blocking the observation.
Right.
And so they did actually measure the deviation. So the star would actually be visible for longer than it should have been if the light had traveled in a straight line. And it reappeared sooner than would have been expected as well.
Okay.
And you measure by how long you measure the delay, and you compare that with the predictions of Newtonian and Einsteinian gravitation and Einstein winds.
Okay. So when you talk about these massive objects, then this would not necessarily be Earth or the moon-sized massive. These are going to be much, much bigger than that, right?
In what case?
When you were talking about massive objects reflecting light.
Oh, well, in that case, it was the sun.
Okay.
So then other predictions are gravitational mirages. You know, when you see multiple images of a single object behind a massive object. So those were also predicted by Einstein, but he thought that it would be too small an effect to be observable, and he was wrong on that. There are amazing images of galaxies appearing in multiple copies around another massive object, and that is not just interesting from a theoretical point of view. It's also interesting because by measuring those images and so on, you can actually infer the mass of the object that did the deflection of the light. And you can also sometimes, in some cases, observe a supernova going off in those cases. Right. And the amazing thing is that the time the light takes to travel can be different in the various images because it travels for a longer distance. Okay. Which means that you can see the supernova exploding at different times.
Oh, that's kind of cool.
So and you can infer a lot of interesting things from that.
It's almost like you get like free time lapse photography from that effect.
Yeah, but it also means that if you catch it in time, you can look at that thing and you know, oh shit, supernova. Let's look here. And catch it from the very beginning and focus on it. And
so galaxies then do spiral around other large objects, like maybe a black hole or another galaxy. Because I thought they always just kind of were moving, not necessarily in an orbit around anything. Or when
they are attracting each other, so sometimes they collide and. You have, clusters of galaxies that have interesting dynamics. The black holes are usually in the center of the galaxies. Okay. You have those huge supermassive black holes in the center. And then you have dark energy and dark matter that also affect the dynamics of all that. We do have one question, actually, from Regis. Question is, do you think we'll be able to extract more information than weight from those waves, phase, shift, etc.? Yes. So from the shape of the wave that was detected when those two black holes collided, I think it was possible to infer the sizes of both black holes, and I don't know if they were able to infer much more than that, but in principle, yeah, they should be. So yeah, actually no, that's not true. They were able to observe how fast they were colliding and. A lot of interesting points of data about the dynamics of the collision. what else? Yes, another verification of general relativity is the that paradox where two twins, you take two twins, one of them travels away in space at a
One
very high velocity and comes back.
old.
And yes, one is older than the other.
Yeah.
Which is a tricky one to understand because it's supposed to be relative. So which one should get older? Because one might think that the other is not moving, and vice versa.
Right.
But actually, that paradox is easily resolved when you do the actual calculation, because one is accelerating, the other isn't, and that is less relative than you might think. So you can make the calculation and determine exactly how older one will be than the other. And we actually made that experiment by sending clocks into space, into orbit.
Oh, I thought you were going to say Matt Damon, and then he got stuck there or something. Okay.
No,
Yeah,
he didn't travel. He didn't
Close.
travel fast enough. I don't know. Well, anyway, and you might be aware that this is fiction, but
no, it's not. So did the clocks get older then, or?
Yes. So perfect verification of general relativity again. And another one is that gravitation affects both space and time, and one of the consequences of that is that a clock that is at a certain altitude is going to tick at a different frequency than the same clock in altitude. And that is also easily verified and does confirm general relativity to a very high accuracy. And it has some interesting consequences. For example, if the clocks in the GPS satellites didn't take that effect into account, your GPS wouldn't work.
Yeah.
And that is just because they are in altitude, so they will tick at a different frequency than the same clock on the ground. So you need to synchronize them differently.
So it sounds like you're also implying that the Earth is kind of like round or spheroid or something like that, and definitely not flat then.
Yeah.
Is that what you're saying? Because I may have heard differently from some famous guy in the last couple of weeks.
Yeah, let's make another episode on flat Earth, because that is going to be
just
so
a mock that
funny.
dude, but yeah, just okay.
Yeah, we should absolutely do
All
that.
right, so we'll have to point back to here in that part where you said that it might be round. I'm not so sure about this yet.
Yeah.
Okay. Yeah. Because I look out on the horizon and it pretty much just goes like that. I don't see what the problem.
Yeah, I know. Let's talk about that another time.
Okay. I know this could go on for another hour and a half if we start on this.
Yeah, actually, I think we've pretty much covered the gravitational waves topic. I think we can pretty much stop here for today. This has been a lot of fun, and hopefully they're all going to be like that. I hope this is entertaining to everybody else watching. Thanks, Rachel. So one thing we do usually is that we also talk about biases and logical fallacies. We're not going to do that today, but yeah, we'll do that next time.
Okay.
Cool. Well, I guess this is it. We actually have a show that is
now
online and that people can watch after a year. So that's exciting. And I want to say that I'm entirely responsible for those existing shows being stalled on my hard drive because I need to find the time to actually edit them. But what's great about this is that there is no editing, so you get you get the raw conversation, and you get it with all the errors and inaccuracies and
bloopers and everything.
Yeah, bloopers and everything. So thanks for watching, everyone. Rachel, we'll talk again next week, unless we put a canned one online. We'll see.
Right.
But
so
we probably won't have such big news again next week. But
I know. Oh well.
All right.
Cool.
Thanks.
Bye.
Bye, everyone. See you next week.